All right, folks, so we're going to go ahead and do the impulse, and then we're going to go ahead and look at number 8. So, impulse, I think this is probably what you're talking about right here, would be number 3. So, effectively, the chat would open for me, but I guess it won't. That's cool. Oh, there we go. Awesome. So, now if we come back to our equation slide, we're going to see that our impulse equals the change in force multiplied by the change in time. Okay, so if we go back to our review, literally, so that's 1,000 newtons, that's the change in force, and it's over 2 seconds, change in time. So literally the answer to this one is simply 2,000. Sorry, the chat's not coming up like it's supposed to. Oh, that's not great. Okay, there we go. Awesome. Okay, so then let's go ahead and take a look at number 8. And number 8 is how much force we need to produce to push a 100 kilogram block that has coefficient of friction of 0.9. So remember, our total force that we're going to need equals our coefficient of friction multiplied by our actual normal force. So in this example, we're talking about a block that's just pushing straight down. So we're going to take that 100 kilograms, multiply that by 9.81 meters per second squared. Force equals mass times acceleration. So we have the mass, we multiply by the acceleration of gravity. So now we have the force. So then we take that, which will be 981, and multiply that by 0.9, and that's going to give us the total amount of force that we're producing. Okay, so for power, how do you convert the kilogram to watts? Now, the key is, it's not so much that you can convert into watts, you have to go ahead and obviously run the math on the other components. So, first thing we need to have when we're looking at power is, well, understanding what all types of information we're going to need. So when we look over here at power, guys, power equals work divided by time. And work equals the force we're producing times the distance in meters. So if you're starting with just the mass, you don't even have a force yet. You need to take, obviously, the mass multiplied by the acceleration. That is going to give you the force. Now you're going to multiply the force by the distance you're going to be moving that object. Then you're going to take that force times that distance and now divide it by time, and that's going to give you power. So it's one of those A, then B, then C. The key is you simply need to think about what units are you starting with, and then what units do you need at the end. And you should always have everything you need. It just might not be the simple and clearest thing for you to approach. All right, so number 2, if a 70 kilogram athlete runs along at 5 meters per second and hits a cart that weighs 50 kilograms that he pushes along with completely preserved momentum from the previous moment, what velocity will he be moving along at then? So the idea here would be someone is running along, they hit the cart, and then they and the cart are moving together, okay? So remember that momentum equals mass times velocity. You have their mass, 70 kilograms, you have their velocity, 5 meters per second. So their initial momentum is 70 times 5, which is going to give you a grand total of 350. Now, once they hit that cart, now they're going to have a system mass, meaning both them and the cart, of 120 kilograms. And our question is, what is the velocity? So all you have to do is if M1, the initial momentum, equals M2, the secondary momentum, so we've got 350 for that sum, equals 120 times velocity. So we're going to divide both sides by 120. So you get 350 divided by 120 equals our current velocity, which is going to turn out to be just a little bit less than 3 meters per second. Because obviously now they are much heavier than they were beforehand, but they are preserving the momentum. Does that make sense, Joyce? Awesome. All right, number 6, how much power would you have produced if you lifted 200 kilograms upwards 2 meters in 1 second? Okay, cool. So first thing we need to do is figure out force. So we take 200 kilograms, and then we're gonna multiply that by 9.81, the acceleration of gravity, okay? So right then and there off of the cuff, we're going to now have our force. Then we need to multiply that by the distance. So you're going to take that 200 times 9.81 times 2 meters, because that's how far we've gone. And now we have our work. So in order to figure out power, we take that work divided by time. In the examples that we're using with Earth gravity, yes, Catherine, it's going to be 9.81 meters per second squared. That's why it's literally sitting at the top of the review. For now, I'm trying to keep it so that we're only doing these problems effectively for being on Earth. So, what other questions you guys want me to go and work through? All right, number 25. An object starts traveling at 15 meters per second and decelerating at 2 meters per second squared. How far will it have gone in 5 seconds? All right, so remember our distance formula. So we're going to have our initial velocity times time. And then in this case, because we're deaccelerating, it's going to be minus 1/2 of the acceleration times time squared. And then if we add plus or minus that or otherwise, but that's a 0 because we just want to know how far it's gone. So 15 is our initial velocity, time is 5 seconds. So 15 times 5 is 75 meters. Now we're going to subtract from that 75 meters 1/2 of the 2 meters per second squared acceleration. So we have 1 times time squared, which is 5 seconds, and 5 to the second power is 25. 25 times 1, still 25. So 75 minus 25 gives us 50. The object would have gone 50 meters in 5 seconds. Now, for the following question, which is if an object starts traveling at 15 meters per second, deaccelerating at 2 meters per second, how fast will it be going in 5 seconds? So for this, our current velocity equals our initial velocity, v sub o, plus our acceleration times time. Now this is a negative acceleration, so it's going to be 15 minus 2 times 5. So 2 times 5 is 10. 15 minus 10 is 5. So the current velocity for it for 26 is going to be 5 meters per second. Cool. Could we go over number 7? Yeah, Luke, give me one moment. If an object has a coefficient of restitution of 0.5 and is dropped from 7.5 meters up, how high will it bounce in the second bounce? Okay, so remember, coefficient of restitution is effectively how much it's going to bounce off the ground from its initial bounce. So after one bounce, it's only going to jump up, or it's only going to come up half of that 7.5 meters. So that means it's going to bounce 3.75. Now, from that 3.75 meters, it's only going to bounce up half of that. So that means for the next one, it's going to be about 1.6, gosh, what does that end up being? 1.675 or so. So effectively, all you're going to do is take 7.5 times 0.5 for your first bounce, and then times 0.5 again for the second bounce, and that's going to give you the height. No worries, guys. We can keep talking about whichever of these you guys want to go ahead and work through. And remember, guys, when you're taking the quizzes, when you're doing the tests, always, always, always make sure that you have your equation slide pulled up. You can print it off and have it next to you. You can write it all down in a notebook. Whatever method works for you. The key is, I have no interest in making you guys memorize the formulas. I've just had to do them so many times that I've memorized them. But instead, making sure that you guys understand how to apply the information. That's the big key. All right, so number 12. What is a horizontal force vector for a ball thrown with 800 newtons of force in a 30-degree angle? Okay, and so 11 and 12 are just using the opposite of our wonderful trigonometry signs. So for a 30-degree angle, okay, and 800 newtons is our hypotenuse. So we have then our adjacent angle, and that is going to be our horizontal. And then we have our opposite, and that's going to be our vertical. So we're going to need to utilize sine. So the sine of 30 degrees equals our vertical force vector divided by the hypotenuse, which is 800 newtons. So we multiply both sides by 800 newtons. So now we're going to go ahead and have 800 newtons times the sine of 30 degrees equals our vertical force vector. And so in order to find the horizontal force vector, you would simply use cosine instead. Good, good. All right, so I'm going to go ahead and give you guys a trick question, okay? And notice I start off by saying it's a trick question, okay? Now, if, let's say, for example, that a 100-pound person is squatting 150 pounds and a 200-pound person is squatting 100 pounds, who is lifting more weight? So 150 pounds being lifted by a 100-pound person, 100 pounds by a 200-pound person. Who's actually lifting more weight? The 200-pound person. You're correct, Catherine. Now the question is, why is that? Exactly. So when we're looking at movements, and this is something that is, it's an important concept, but don't worry, you're not going to have exam questions over it, but I want you guys to think about it, is what's known as allometric scaling. So the issue is the bigger you become, can be obviously due to muscular bulk, the greater amount of mass you have to lift that isn't just the object you're trying to move. And that's why, you know, for example, I'm sure, are a number of you guys aware of Hafthor Thorson's, I think it was, yeah, 501 kilo deadlift, which literally means like, it's like 1,102 pounds, something, you know, relatively absurd. Or you guys can throw that up in the poll. Have you guys heard of that or seen that or anything like that? Okay, well, give me a second because we're about to educate you guys with crazy strong people. Okay, so yes, Luke watched it. I saw the replays later. I mean, it's cool. It's a whole lot of weight. Okay. Okay. Nope. Luke, I'll tell you what, it always looks like you got more in you than you really do, because those type of movements take it out of you. Okay, so real fast. And I guess it's not going to be that fast. Okay, so this right here is Hafthor Thorson. I believe he weighs about 440 odd pounds. Yes, he's using straps, but that's typical in strongman. That's completely allowed. And I don't even think he's wearing a deadlift suit. I think he's just in a t-shirt and shorts effectively, along with wearing a belt. So that is that 501. And I will agree that it was smooth. There wasn't a question over whether or not he got it. Maybe a slight hitch in there, but it's strongman. So, yeah, definitely kept it close to himself because he bled all over the bar. Now, here's the thing. That's freaking awesome, and that's really impressive. Hafthor weighs, like I said before, guys, I think it's like 400 and some odd pounds. That is 1,100 pounds. That literally means that his deadlift is just shy of being 3 times his body weight, which is freaking awesome. Don't get me wrong, it's a world record. Now, thanks to allometric scaling, he's lifting not just that 1,102 pounds on the bar, he's lifting that 400 plus pounds himself, and he even chose to wear a hat, which I don't know why, because that's going to add even more weight to yourself, and I try to avoid it. Oh, and he actually looks like he's wearing not just a lever belt, but he's also wearing some reband, so that's kind of cool. Now, here is my personal, or one of my personal heroes when it comes to lifting, by the name of Lamar Gant. Lamar Gant, notice, is a 123-pound power lifter. And I think it's probably going to go with the bench press, but no one really cares about that, because the thing that Lamar can frickin' do is this deadlift right here is 634 pounds. He weighs 123 pounds. Which literally means in that deadlift you guys just saw, and I understand obviously it's older, this is I believe late 70s, definitely early 80s when he pulled this off. Lamar literally deadlifted over 4 times his body weight. And that, I don't think pound for pound anyone's ever done anything better than that before or since. Yeah, exactly, Catherine. So think about it. If Lamar could pull off his 4 times body weight deadlift at a body weight just larger than my own, meaning like he'd be like 220, he would literally be deadlifting over 1,000 pounds, which is Fruit Loops. But, you know, part of that, like I said, is due to allometric scaling. Notice Lamar is a much, not just smaller as in lighter athlete, but he's also much shorter. And then what's really fascinating is he has really bad scoliosis. And I believe his best deadlift ever, I think he pulled close to 700 pounds as like a 143, 145 pound lifter. And he was definitely a mid-5 squatter, and he was almost a 300-pound bench presser at a body weight of that small. So hence allometric scaling is a factor in sport, and body weight relative strength is an important concept to keep in mind. And obviously the other component is think about work. Half War is 6 foot, God, I think he's like 6'7", 6'8". He's a very, very tall human. He's walked by me a couple times at the Arnold, and I'm just, dear God. He's a massive human being. Lamar, I think, is, I don't know if he's still alive. I imagine he is. He, I think, is only like 5'5" or 5'4". So he literally just doesn't have to pull the bar as far. So, fun stuff with lifting. I can easily pull up videos of people picking things up and putting them down all day because it entertains me. But does that make sense when we talk about allometric scaling and then effectively how much load someone's going to have to lift relative to another individual? And so it's really an important thing if we're talking about application of biomechanics of when you're training your athletes or you're training yourself or anyone else, is thinking about what's the range of motion difference that you're going to find between your athletes. Because literally, if you have an athlete that is markedly taller than another and they're both using a full range, the taller athlete is going to be doing significantly greater work each set due to that range of motion. And then also keeping in mind how loading is going to affect all, things like joints and otherwise. So what other questions would you guys like me to go ahead and talk our way through? Number 20. Yeah, at some point I'll pull up videos of David Riegert and just fanboy all over it. Oh, cool. So which would hurt more? Pressure. Remember, pressure is going to be that force divided by area. Getting hit by a softball that weighs 0.25 kg or getting hit by a baseball that weighs 0.15 kg. Now, the key is with both of these examples, we are going to notice we've got kinetic energy. So we're going to go ahead and have 1/2 of the mass times the velocity squared. So the first thing you do is solve for the kinetic energy of each of them. So 0.25 times 10 squared, which is going to be 100, and it's 1/2 of that. So 0.25 times 0.5 times 100. So you end up with not that big of a number. And from there, you're going to do the same thing with the baseball of that 0.15 times 10 squared times 0.5. Now, you're going to figure out which one gives you the greater amount of pressure. So you're going to take that initial kinetic energy of the softball and divide it by 0.024. That's going to give you the pressure that it produces when it hits you. Then we're going to do the same thing with that kinetic energy we got from the baseball, only divided by 0.0136 because a baseball is obviously much smaller in diameter. And so from there, now we have the pressure for each of those, and it's simply going to be which one's higher. No worries. What else can we work our way through? All right, number 13. How much force do you need to create to move a block with a static friction of 0.9 and a dynamic of 0.8 if it weighs 800 newtons? So the good news is we don't have to convert from mass into force now. We've already got the normal force, 800 newtons. Now, notice it says to move a block. So that means the block is effectively at a dead standstill. Where it was 14, notice it's the exact same, but it's to keep a block moving. So that's going to be dynamic friction. So static, remember, is at rest. So it's literally going to be 800 times 0.9 gives us the amount of force you need to get it to move. Now, to keep it moving, that's going to be the 800, or sorry, in this one, it's a heavier block. It's 4,500 newtons. We're going to multiply that by 0.8 newtons, and that's going to go ahead and give us the total amount of force that is required. No worries, anytime. What else you guys want to talk about? Any other questions here, or just kind of in general about the wonders of biomechanics that you're interested in talking about and working our way through? All right, well, seeing as how could we just discuss the question on spin? Yeah, remember, spin is important because if we know the spin of an object, it's going to give us information about how it might bounce, how it might curve when it's going through the air, and then effectively, what type of changes are we going to see naturally on its velocity. So right now, we're not talking about spin as in a true mathematical formulation of looking at what's going on with a greater amount of drag on one side compared to the other, which causes that change, but instead understanding that we care about spin because it's going to give us an idea about how an object in motion is going to play specifically when it's a projectile. So the one above it, it says, why do force vectors matter? Well, it turns out it's going to be a direction and obviously a amplitude of force. And if we understand how and where we're applying force vectors, we can have a good idea of, is our athlete being as efficient as possible? Is our athlete being inefficient? Is there a way that we could produce more force? And think about the running out of the block example that we gave you guys, the amount of force that you would drive yourself forward to the 500 newtons. Well, if you try to put all that force directly behind you, well, at the lowest angle you can, so trying to be like just 2 or 3 degrees off the ground, well, you're applying so little force vertically that given your amount of body weight for pretty much everybody in the class, you're just going to lawn dart yourself. You're just going to kind of leapfrog into the floor. So you always need to have enough vertical force to keep your body up, but then you want to maximize the horizontal force vector when you're trying to run forward. So we have an idea of literally what is our best start position for an athlete. So a much weaker athlete needs to start a lot more vertical. A very powerful athlete can start with a much lower angle of their body whenever they get going. And then the same thing when it comes to eventually, sometimes you can think of it as the term force leakage. So it's a point where we're not able to transmit force to the body appropriately from one area to the other. And the other concept is just inefficient force production. The reason I say inefficient sport production, not that a lot of you guys have the opportunity to play sports with friends, but if you ever get a chance, and this could be something you could kind of do for fun, so to speak, in a weird way, but stand behind somebody when they're sprinting or directly in front of them. Your most efficient athletes, whenever they're going to go ahead and be trying to run at a maximal speed, you're going to effectively see, if we're going to look at that force vector, every single leg that they hit the ground with is applying the force directly forward into the ground to move them forward. Okay? And they're actually going to have their feet apart. So their feet aren't going to be running on a straight line. Instead, they're going to be running straight underneath the hip because they've got the amount of power and stability at the hips that they don't have to fall underneath themselves. Weaker people have to do that. Now, the other thing you're going to see is when you watch some people run, they'll have their feet turned inward, or they'll have their feet turned outward. And so, or they could be running with a really wide-legged position. So if we're running with this wide-legged position, where we have to have these force vectors pointing us back into the middle, what we're really doing is every single step, we're wasting this amount of force. And that wasted force is wasted effort. The wasted effort is obviously not going to allow us to go at what is our truly maximal speed, because our force production is not being performed in a way that's going to allow us to move efficiently. So hence, why we care about force vectors is simply because it allows us to deduce, is our athlete as efficient as they can be for what we're trying to accomplish. Oh, sorry guys, we're about to have some fun. Oh man, we're gonna have some fun. Okay, I was really hoping that I'd have an excuse to bring up David freaking Riegert. Oh man, he is my, hands down, my favorite Olympic lifter of all time. And the reason is because he was freaking intense and insane. The thing about Riegert is he was known for literally taking shots at world records, whether or not he was in shape for them, ready to go or otherwise. He would just let it frickin' ride, which there's just something about that to me that's just awesome. Now, we're going to watch David Riegert lifting because it makes me happy. But more importantly, because now when I'm talking about the efficiency with force vectors, I want you guys to go ahead and really, and I'll talk it through as it's going on, but this is David Riegert. He was a heck of a lifter also in the 1970s. The man looked like he wanted to rip the head off of a lion, and yes, he did lift. And he actually recently was the coach for the Russian Olympic lifting team. Okay, so of course, we got to have the awesome onesies shots and otherwise, because that's what they used to compete in. Sorry, let's get to where he's actually picking things up and putting them in. Oh, yeah. Supposedly, the first time they saw his back like that in America, they called him a stegosaurus. Notice he had to come forward. That means when he lifted that bar, he did not keep it completely vertical with his force vector. He had to shoot forward with his body to go ahead and go after it because he didn't lift it vertically. Whereas this, with a clean and jerk, you're going to see how he keeps that through his body line, and it's super efficient and easy to do. By easy to do, I believe that was like 400 something pounds, and he was only a 200-pound lifter. He misses that snatch and falls forward onto his knees and then just smiles and jokes to the judges. So again, the force vector's in front of him, because the problem is when the weights get to be incredibly heavy, folks, it's really easy to make mistakes and specifically have that bar go out in front of you because you weren't perfect with that force vector. Notice there, it was behind him. He had managed to put that bar and somehow pull it backwards with himself as he was going. Dear God, it's just so awesome. Yeah, and you can see a little bit of force leakage there with that right knee buckling in a little bit, of not as efficient, but once again, that's probably close to a 400-pound clean and jerk. It's got like really cool Russian music playing in the background, but I figured I would save you guys from that. So right there, you can see how the weight's out a little bit in front. He has to go after it, but he was stupid strong. You can actually see his freaking TFL right there, which is just insane with how lean he'd be. One interview I read of him, he literally never maxed on the back squat, but he's like, yeah, once I could squat 600 pounds for a set of 5, I figured I was strong enough. Yeah, that's 220 kilograms. So that's, yeah, about 400 and, yeah, about 485 pounds. Notice force vectors, it's in front of him. That's why he's got to go after it. Ah, man, freaking Riegert. Any excuse to watch videos of Riegert lifting. Any excuse. Any other questions you guys want me to go ahead and work through? Take your time, guys. Go ahead and look through the homework and see if there's certain things that you're not quite sure about. All right, sounds good. So let's go back to share screen. Sorry, just one more little fanboy thing for bigger. This is what's known as the clean and press. You would it was a competed lift in the Olympics, in Olympic lifting until the mid 70s, where literally you would clean the bar up and then you would press it. Now notice these guys would lean back, and they removed it because they realized it probably wasn't the safest and kind of was easy to cheat it a little bit. Rieger could press 400 pounds overhead. So anytime I think I'm kind of hardcore and I'm awesome, remember the fact that literally this guy and a number of other Russians could take 400 pounds and press that overhead in one motion. Yeah. And he would also screw with his competitors by doing maximal attempts in a warm-up room with either his feet together or also do it barefoot on occasion. And just so we're clear, guys, the reds are 25 kilograms each, meaning 50 kilos on each side of the bar, and that's probably a 5 kilo plate. So you figure that's 130 kilos, and he's yeah, just rocking the briefs. So crazy. All right. So to finally get at your question, Cassandra, with number 5, how much work have you performed if you lift 200 newtons of force, 2 meters for 10 repetitions? So this is a good thing to understand because it helps you understand the total amount of volume that you happen to be doing. And the key is anytime we're doing any exercise, you know, our muscles are obviously doing the work, our joints and our bones are having to transmit that force. And so we need to have a good operating idea of literally how much work we happen to be performing. So literally 200 newtons, so that's our force, times distance, 2 meters. So each rep, you do 400 Newton meters of work, also known as 400 joules. Now you're doing 10 repetitions of it, which means you are going to be doing 4,000 joules of work, because obviously you're just taking that 400 joules times 10, okay? Now, why this matters is getting back to working with our athletes. So you're going to, let's say you're lifting weights. You're gonna go in, you're gonna, yesterday I had to get in some accessory work over at the rec, and there were a number of bros squatting 135 to 155, and they were trying, they're putting in, you know, I mean, they're trying. So 155 pounds works itself out to being pretty much nearly dead on at 70 kilograms. And we're just going to go with the external load. So before we introduced what's known as the system mass. So when we have the system mass, you've got the internal load, and then you have the external load of what you're actually lifting. So for this, we're only working with the exterior load, okay? External load. So if you're doing that, they're squatting 70 kilograms. Gravity is 9.81. Now, when you go down and back up, you have obviously a negative and then a positive acceleration. But if we took the average acceleration, it's going to be just the acceleration of gravity. That's why it kind of effectively mutes itself out once we go ahead and look at these math questions in certain contexts. So you take that 9 0.81 meters per second, multiply that by 70 kilograms, okay? Now we've got the effective force that they're actually having to provide to lift that barbell. Then we're going to say that the range of motion was 1 meter. So take that 75 times 9.81 times 1, and we have the amount of joules of work they have to perform to do 1 repetition. So if they did 3 sets of 10 there, that's going to be 30 total reps. Boom, multiply it out again. We've got the total amount of work that they would have done over that entire session. And so when it comes to muscle size, not necessarily muscle strength, a lot of muscle size is simply related to how much volume of work you're doing. So that is literally the joules of work you're making that muscle do. Yes, it needs to be at a high enough intensity of your maximal contraction, but there's research showing that even if you're lifting at really low loads, meaning it would be something like only like 20 to 30% of your maximum, if you're taking that to failure, you can still gain some muscle mass. So when you're working with athletes, training yourself, training anyone else, we need to keep in mind how much work we're performing. And so another easy way to figure out, not easy way, but an interesting way to look at your work is to like count your steps. So if we know how many steps you take in a given day, we know effectively how much you weigh, then we can get an idea of literally how much work your body is used to. So for those of you guys that wear like a step counter, Garmin, Fitbit, Apple Watch, anything there that tracks your total activity, if we were to take how many steps you take every day, and then tomorrow I wanted you to double it, triple it, quadruple it, you'd probably be sore from doubling it and definitely for tripling it. And yeah, I'm 100% confident if you quadrupled it from what you normally do on average. So if you normally do 10,000 steps a day, if I had you today, you have to put in 40,000 steps, which you guys better get after it, because that's, that's gonna be pretty close to walking. It should be walking well over 20 miles. I don't think you're getting up to 30 depending on your stride length, but that's just a lot of work. And so that amount of work induces stress on your tissues, stress on your muscles, and so on. And that's what's going to lead to the wonderful soreness that you can get. So, sorry for going off the rails a little bit there, Cassie. Sorry, Cassandra. Do you like to go by Cassie or do you prefer Cassandra? Okay, Cass, perfect. Any other questions you guys want me to go and work my way through? We always can watch more videos of David Rieger lifting. That's always on the table. Okay, so to kind of wrap up, we're going to be obviously getting to the far end of this. The next lab you're going to be doing is anthropometrics. So we're really just looking at the length of different body segments. So we're going to have you measure, obviously, how tall you are, how long your arms happen to be. Dear God, my arms are long. I have to walk out of the fray. How big your hands are, how big your feet are, how long your shin is, how long your thigh is, how long your torso is. And that's going to be useful because from there, you're going to be able to figure out some lever arms and some lengths that are going to be important when it comes to doing the math on your activity that you're breaking down as a group. So for those of you guys, some of you guys probably have like a fabric tape measure where you can literally, just put the loose tape measure there and you can figure out the length of the section. That's great. For those of you guys that do not have that available, the method that I find to be the best way to go about it is get a string. Get something that happens to be of a length that you can easily work with. It could be take off and use a belt, anything along those lines where you can figure out the length of that segment. From there, then you're going to get a ruler. And if you really need a ruler that badly, we have them in the lab. I'll effectively leave them out, probably literally on a table in this classroom. I'm talking from room 221 right now. So then you guys are going to be able to measure the length of that segment by literally just like, okay, I did that much of the belt and that was X number of inches. So we're doing this to, once again, help us get a working idea of just limb lengths and everything relative to yourself, which is then going to be useful when you guys are working on your project. So any questions over that lab and kind of expectations there as far as the ways to go about it and measuring? Well, Luke, the good news is when you got T-Rex arms, it makes the bench press really easy because you don't have to move the bar so far, but boy, howdy, deadlift is not your friend when you're built like that. Anything else you guys want me to go and cover for the day? Otherwise, you know, I mean, this is still your review. One thing real fast, let's just go ahead and take a poll over it because we've been moving more rapidly than I normally would move through this material. And I doubt it's because I'm doing a great job of teaching it. I just think more or less because we don't have the back and forth we naturally have inside of a classroom. So if you guys want, we can go ahead and kind of, we'll work ahead a little bit in lecture next week, but we will still allow time to review as we go through. So you guys will, we can either have you guys take the exam next week or the following. So if you want to take the exam next week, then go ahead and just hit yes on the poll, and whatever the majority says, that's what we're going to go with, guys. So otherwise, we can push the exam back 1 week. It's your guys' choice. So yes means you want to take it next week. No means you want to take it the following. I also like using the polling because it lets me know how many people like just have the, they signed into Zoom and then just kind of walked away, and how many of you guys are actually at the computer, which, and or how many people know how to use the polling thing and or have a way to hit that button depending on what they're streaming from. So there's a lot of different things that could be going on. But the no's definitely have it. So, okay, we're gonna work ahead. We're gonna talk about kind of defining sport skills and the way that we're gonna move through, the way that we're gonna break down movements next week. So we're gonna be working ahead with the lectures, but don't worry about taking the exam until the following week. So we're going to plan on effectively lecture Tuesday, lecture Thursday. Next, not this coming Tuesday, but the following Tuesday, we will not have lecture at all. Just going to take the exam. And then Thursday, we're going to go ahead and go through it. Yes, Haley, the exams are going to be very similar to your quizzes in that they're going to have some multiple choice. However, for your exams, you're going to have short answers, and those are typically going to be your math problems. Every time you guys have those problems, the key is set it up. Show me the formula that you used. Show me the numbers that you put in. I will give you partial credit as long as you can show me your reasoning. Now, if you just know the answer dead to rights, it's, you know, one of the easier ones on here, like the impulse, it's just the 2 seconds multiplied by 1,000 newtons, so it's 2,000, boom, done. And make sure you always put the units on there, then yeah, just put that in there. Don't even show me your math. But for the more difficult ones, like we're talking about power, like, okay, you know, make sure you put the power equation on there. Make sure that you're showing how you got your math and how you came to answer, because it's easy to mess up your order of operations. It's easy to make a mistake, but if you at least show me that you set it up correctly and you maybe came to the wrong answer, you're definitely gonna get partial credit. If you set it up improperly and you at least tried and yeah, you were wrong and that's okay, you'll probably get some, for lack of a better term, we'll call it mercy points, where it's probably like, yeah, you gave it a shot, you know, 1 or 2 out of 5. Like, and that's just arbitrary numbers out there, guys. So, because like anything else, I want you guys to be rewarded for effort. Don't get me wrong, you're going to get a better reward for getting it right than just putting in the effort. So, you know, make sure that you're going through and showing what you came up with, how you came up with it. And if it's a kind of a short answer essay question, like obviously we talk through the force vectors and we talk through the spin, that should be a couple sentences. They should be explaining the information. So there's a variety of different types of questions. You know, you're going to have, once you click start, X amount of time to do it. And remember, you're going to take it once as an individual and then once as a group in your activity groups. Only one person per group needs to take the group exam, because I'm just going to copy over the grade that that person got into the other members of the group. Otherwise, yeah, guys, the study guide that should be your study guide is really true to form of what you're going to find on the exam. So if you understand all these questions in a theoretical sense, meaning you understand the formulas you use and you understand how you apply the formulas, so AK, the numbers can change, but you know how to set it up anyways, you're going to do fine. If you cannot answer a number of these questions, you don't even know how to start to break it down, you're going to struggle on at least, especially those questions. So I really try to make the study guide, for lack of time, or lack of a better term, telegraphing my shot so you can really see, like, this is the type of question I'm going to ask you, and you should be prepared to answer those questions. So you feel, well, maybe not necessarily feel better about the exam, Haley, but you feel better with kind of having an understanding of the format you're going to see? Awesome. Good, good, good. You guys okay with getting out early, or you guys prefer that we talk some more? We can review more on questions. Guys, if you haven't had a chance to sit down and do the study guide, sit down and do the study guide. Go through it. And then, like I said, on Tuesday, aside from lecturing, we're going to go through and talk about anything that you guys were like, wait, hold on, how do you set that up? Or like, is this right? More than happy to go ahead and keep going through the stuff. One thing that obviously sucks for me on this, well, it's good and bad. It's good in that when I teach this class normally, and I kind of, obviously, you know, we have students in the classroom, when we start talking through the math, I see like the look of like terror in people's face, which really scares me. Like, I don't like looking at people that are looking at me afraid of me, because that's not the goal. The goal is to teach and help you guys understand, but it's a great indicator that people aren't understanding it. Right now, when we're doing this over the internet, I don't have that type of, you know, information that I'm getting from you guys. So I'm obviously kind of just like the rest of you guys, just doing my best given the set of circumstances we have. And I want to make sure that you guys understand this information. And the only way that I can know, aside from throwing out the poll on occasion, which is when you guys throw it up in the chat, or you mute yourself and you ask me these questions. Because otherwise, I'm just under the assumption that you guys are so bored and I'm so boring that a lot of you guys have already fallen back asleep, which, I mean, I can't judge you for that. I should probably try to bring a little bit more heat, but, you know, we're working on it. We're trying. Any other questions, comments, concerns? Well, stay safe out there, guys. And I will see you guys on Tuesday morning. And yeah, feel free to tell your other classmates that we're pushing back the exam, or you can choose not to, so they take it earlier and kind of panic, because you can take it whenever you want. You can take it ahead of time if you'd like to. The key is when you do take it as an individual, I want you to wait for the rest of your group so you guys can take it as a group together. Now, when it comes to taking it as a group, worst case scenario we can do is that Tuesday morning, we'll set you guys through Zoom, set you into the breakout room so you guys can be just in a Zoom call with one another. Otherwise, you guys should have each other's emails. You can exchange phone numbers if you're comfortable with that. And then you guys can just meet over, I don't know, a group phone call or whatever works for you guys as a ways that you guys can, you know, share it with one another and make sure that you're all on the same page. So, all right, guys. Well, be safe out there. Take care of yourselves. And I will see you guys on Tuesday. Have a great day, guys. Bye-bye.